Welcome to AI for Good, the leading action-oriented global and inclusive United Nations platform on AI. Organized by ITU in partnership with 40 UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end, as we will hold a 30-minute networking session in the neural network. Here you can meet, ask questions to our distinguished speakers, connect, and chat with the AI for Good community. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you so much, Anna, for introducing the session. Welcome, everyone. Good morning, afternoon, and evening, depending on where you're connecting from. My name is Thomas Pascal from ITU, and I would like to welcome you all to this AI Machine and 5G Challenge webinar session. In this session, we are privileged to have our colleague, our friend, Xingqin Lin, who is a senior 3GPP standards engineer at NVIDIA Corporation, USA. Before joining NVIDIA, he spent 7 years at Ericsson, and in this period he had several positions, and recently it was master researcher, whereby he was leading the 5-6G research and standardization in focus areas. He was a member also of Ericsson Next Generation Advisory Board, collaborating with Ericsson executive on strategic projects. He also served as a global juror for Ericsson Innovative Awards. He has received as well several awards. Today's talk, he will provide a state-of-the-art overview of AI in mobile networks, firstly by describing the basic concepts, reviewing the key advances, and discussing in detail the 3GPP standardization aspects, as well as sharing various design rationales that influence standardization. So at this point in time, I would like to welcome Xingqin. Good morning, and welcome to the Machine Learning 5G Challenge webinar session, and thanks for making some time to join us today.
Hello, everyone. My name is Xingqin from NVIDIA. It's my great pleasure to be invited to this amazing event. Thank you for organizing, and thank you, Thomas, for that extremely generous introduction. Today, I will share our NVIDIA vision about embracing AI from 5G evolution towards 6G. I very much enjoy interactive discussion, so please feel free to raise any question. I will be happy to answer as many as possible. From NVIDIA perspective, we believe we are just at the beginning of the age of artificial intelligence. NVIDIA embarked on this journey more than 1 decade ago in many different domains. In recent years, we have been doing research and development on GPU solution for 5G wireless communication together with artificial intelligence. But before we start looking at that work, I would like to share a short video illustrating how NVIDIA in artificial intelligence is already impacting our society in this 3-minute short video. So let me share the video now. I hope you can see the video.
I am a creator. Blending art and technology. To immerse our senses. I am a healer. helping us take the next step. I am a healer, helping us take the next step. And see what's possible.
Wow. Can you really see?
Yes.
Oh, wow.
I am a pioneer, finding life-saving answers. And pushing the edge to the outer limits. I am a guardian, defending our oceans.
Under that, fly-by inbound.
And the magnificent creatures that call them home. I am a protector, helping the earth breathe easier. And watching over it for generations to come. I am a storyteller, giving emotion to words and bringing them to life. I am even the composer of the music. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere.
Okay, I hope you could see the video. Sorry, the Zoom quit unexpectedly during the video, so I had to restart the video. But I hope it worked in the end. So next, let's get to the presentation of this webinar. I hope you can see my slide. Okay. We'll start with a short introduction to AI and 5G. After that, we will look at how NVIDIA AI on 5G solution can help solve some of the most challenging problems in 5G. Then we will discuss the latest status of 3GPP work about embracing AI in 5G evolution, both from next-gen radio access network perspective and air interface perspective. In the end, we will look at the 3GPP roadmap from 5G evolution to 6G at the end of this webinar. So let's start with a short introduction to AI and 5G. Every industry will be transformed and reshaped in the next decade. The immense forces of artificial intelligence, digital transformation, and 5G connectivity are combining, and they will create unprecedented opportunities in business and society. As conventional computing and Moore's law started to hit limits, accelerated compute for both application and infrastructure came to rescue. Accelerated compute started to become an essential element to achieve required functionality and performance. To think of a CPU serves as the basic unit of computing, but to meet the demands of today's machine learning and AI workloads, we must optimize the entire data center from end to end. The new unit of computing has now transitioned to be the data center, dimensioning the right balance of three essential technologies, CPU, GPU, and DPU, to enable scale-out and scale-up computing. The CPU is for general purpose computing, the GPU is for accelerated computing, and the DPU, the data processing unit, moves data around the data center, and they do data processing for data center. AI automates intelligence. We are just entering the second wave of artificial intelligence. The first wave was reinventing computing. NVIDIA, together with early adopters, the internet companies, has been driving the first wave for more than 1 decade. The second wave of AI is happening in the enterprise and at the industrial edge. We need to turn artificial intelligence from computer science running in the cloud to smart AI products at the edge and in billions of connected devices and computers. We call this AI on 5G. Billions of things can be located throughout the network, and data centers will not be connected at all points in the network. A data center where you need it and when you need it. Where does 5G come into all of this? A ubiquitous 5G network will connect these data centers and intelligent things at the data rate, latency, cost, and power efficiency required by the application. The use of artificial intelligence, 5G, and edge computing to enable Industry 4.0 is a key focus for our NVIDIA team. And we will hear more about that a bit later in this presentation. Of course, you're probably already very familiar with the CPU, Central Processing Unit. Flexible and responsive. For many years, CPU were the only programmable element in most computers. More recently, the GPU, or Graphic Processing Unit, has taken a central role. Originally used to deliver rich real-time graphics, their parallel processing capabilities make them ideal for accelerated computing, tasks of all kinds. Thanks to these capabilities, GPUs are essential to artificial intelligence, deep learning, and big data analytics and applications. NVIDIA pioneered accelerated computing to tackle challenges ordinary computers cannot solve. We make computers that enable researchers to invent the AI-powered future, and that increasingly includes the artificial intelligence for future of wireless. Computing requires more than just a powerful chip. We achieve incredible speedups through full-stack invention, from the chip and systems to the algorithms and applications they run. 5G brings new values. 5G redefines the present market and opens new marketplaces. 5G network capabilities go far beyond the previous generations of mobile communications. 5G enables a wide range of new and advanced applications and use cases, for example, in retail, smart cities, healthcare, media and entertainment, transport, and industrial applications. These applications and use cases can leverage a tailored mix of the 5G capabilities to develop differentiated service experience compared to 4G LTE. For example, 4K video on a smartphone uses large data volume and benefits from capabilities such as extreme data rates. Meanwhile, the augmented reality or virtual reality and mobile gaming will also require additional capabilities like low latency and high reliability for good user experience. In short, 5G provides the underlying connectivity for billions of devices, extending the reach of artificial intelligence algorithms and application to all connected objects at the edge, enabling new use cases and new markets. We are just embarking on this evolution journey of 5G advanced. So we are still in the era of 5G and will be for some time as new 3GPP releases are formulated and 5G network rollout continues. However, 6G research is well underway. In order to have 6G supporting a wide range of new and evolving services, the 6G network capabilities need to be enhanced and extended in various dimensions compared to the 5G networks. 6G will place order of magnitude KPI improvements over 5G. For example, 10x user data rates, 5 to 10x improvements in spectral efficiency, an order of magnitude or more reduction in latency, and an order of magnitude increase in connectivity density. Besides further boosting these classic capabilities, we also need to focus on new capabilities related to, for example, service availability, security, and the capabilities of local compute integration. While we're likely to see a move to terahertz frequencies and the network evolves to a holistic communication and sensor network in 6G, many other fundamental technologies will also underpin 6G, such as softwareization of the system, heavy use of software-defined radios, virtualization, and of course, artificial intelligence everywhere. We are now transitioning into the era of big data meets wireless. The massive parallel computing capability of GPU hardware can support artificial intelligence and also the signal processing. GPU hardware will play a critical role in the continued 5G rollout, 6G research, and eventually 6G development. All networks, such as 5G systems, are becoming increasingly complex for supporting various deployment scenarios and applications. The evolution of 5G systems for improving performance and addressing new use cases makes 5G become even more and more sophisticated. So many technical challenges exist in such complicated wireless systems, from system modeling to algorithm development to network configuration and management. In addition, 5G systems generate humongous data. The use of rapidly advanced AI techniques, such as machine learning and data analytics, is critical to managing the complexity, identifying the patterns in the data, optimizing network design, and enhancing system performance, as well as reducing operating costs. To accelerate wireless innovation, we need powerful computing platforms to enable researchers and engineers to combine simulation, data analytics, and artificial intelligence. As NVIDIA, we are developing end-to-end reference designs, both to learn from and to make our products better, and also for others to use in their own research and development. This slide shows our reference design. It's a powerful platform for researchers and product developers working in the area of software-defined radio, 5G, cloud, and in particular, the combination of 5G, machine learning, and cloud. As wireless networks are becoming increasingly complex, the importance of performing accurate simulation for such complex systems cannot be emphasized enough. The software framework at the center of our most powerful simulation methodology is called Omnibus. We have used this in our NVIDIA Drive and Robotics program called ISIC for bringing digital twins to reality and also for tasks such as reinforcement learning for robotics. We won't get into the details of Omnibus in our presentation today, but we believe it has the potential to be a game changer in many facets of wireless research, development, and deployment in the future. One can already find material presentations and demonstration from Ericsson on the use of an omniverse to build a digital twin for 5G networks. Omniverse can enable real-time, physically accurate simulation, virtual reality, collaboration, and realizing digital twins. There's a lot more interesting research to be done in this area. The notion of digital twin has been taking off in many industries, such as smart manufacturing, oil and gas, construction, bioengineering, and automotive. However, digital twin remain relatively new for mobile networks, including 5G. We expect digital twins to be a powerful concept for 5G networks and beyond. One of the machine learning techniques that has proven valuable in multiple different application domains, robotics, for example, is reinforcement learning. Reinforcement learning is a hot research topic in the wireless space, and there are many research publications on using reinforcement learning for handover, spectrum management, network slicing, scheduling, routing, and link adaptation, just to name a few. For several years, NVIDIA research teams have been working to leverage the GPU for reinforcement learning. And here is an example of reinforcement learning used for a toy application, cube manipulation task, and rendered in Omniverse. Digital twins realized in Omniverse, combined with reinforcement learning, have been used to implement robot training tasks. While the training occurring in the digital twin and the learned data used to configure robots in the real-world digital twin. As the 5G rollout continues, digital twins have the potential to assess network performance, predict the impact of environment and system changes, and optimize 5G network configuration, operation, and decision-making process. Next, I would like to introduce you to our NVIDIA Shana SDK, a GPU-accelerated simulation framework for next-gen link-level simulation. Shana is designed for rapid prototyping of complex communication systems, which allows you to go as quickly as possible from a research idea to a first proof of concept. For this reason, Shana provides a wide range of state-of-the-art components that you can simply connect to build sophisticated end-to-end link-level simulation. Shana has native support for machine learning, which means you can easily replace traditional processing blocks by neural networks. And since we need gradients to update the weights of the neural network in our systems, Shana is also differentiable from end to end. Shana has native GPU support, but also runs on CPU. You can scale your simulation by either distributing components of your system on different GPUs, or by replicating the entire system on multiple identical GPUs to increase the number of Monte Carlo simulation that can be run in parallel. We have put a lot of efforts into the API design, which is supposed to be very easy and intuitive to use. And since the entire source code is available, it's easy to build your own components by extending existing ones. All the available building blocks are carefully tested, so you can fully rely on them for performance benchmarking with your own algorithm. And we think this is a quite time saver because you can focus on your research rather than implementing or re-implementing things that your research is not focused, or that might even be outside of your expertise area. And lastly, Shana is free to use and fully open source. Everything is on the GitHub repository that is maintained and further developed by NVIDIA. And we hope this openness will lead to more reproducible research in our community and encourage many people to do the same, to contribute components and to make their Shana-based research results available to others. Okay, next, I would like to introduce our NVIDIA AI on 5G platform and solutions. Our NVIDIA platforms and solutions have been deployed in countless cloud applications over the past decade. Increasingly, more customers are looking into AI at the edge or device-based artificial intelligence to enhance their products and services and to transform their workflows. Through the EGX Enterprise platform, NVIDIA is extending our AI know-how into the enterprise compute sector. NVIDIA AI on 5G is a unified platform that brings together developments in artificial intelligence and 5G at the edge to accelerate the digital transformation of enterprise across all industries. We are at the dawn of a new era of industrialization driven by artificial intelligence and digital transformation. The data center is the new unit of compute, and the data center will be where you need it and when you need it, as we mentioned at the beginning. The data center will be connected through a high-performance 5G network, a network that is driven by AI to be energy and spectrally efficient and self-organizing. So these technologies come together on the NVIDIA AI on 5G platform. This will drive innovation and kickstart the next industrial revolution. This slide shows the end-to-end block diagram of NVIDIA AI on 5G platform. Starting from the left, we have the many different types of 5G devices that can be connected to the platform. Going to the right a bit, we have the 5G radio. The all-round radio unit implements the digital front-end signal processing. It also implements lower layer physical layer functions, including OFDM modulation and demodulation, and some aspects of beamforming. Continuing to the right, we have the AI on 5G hardware. Here we have compute resources, the GPU, for signal processing and machine learning. The 5G network interface card supports the front hall interface, and CPU hosts for layer 2 functionalities. The rightmost figure shows the AI on 5G software. At the bottom, we have NVIDIA management and orchestration solution, such as Free Command, that securely deploys, manages, and scales AI applications across distributed edge infrastructure. Moving up to the stack, we have NVIDIA Aerial 5G. Here we have CUDA baseband, so-called CUBB, and CUDA virtual network function, CUVNF for short. So CUBB provides a GPU-accelerated 5G signal processing pipeline, including CU5 for layer 1 5G physical layer processing. CUVNF provides optimized input-output and packet processing, exchanging packets directly between GPU memory and network interface card. The next layer highlights NVIDIA AI enterprise solutions, including Doka, CUDA, vGPU, and Magnum IO. On top of that, we have NVIDIA Unified Computing Framework. UCF is a fully accelerated framework for developing real-time AI applications. At the top layer, we have NVIDIA application frameworks. For example, Metropolis is an application framework that brings visual data and artificial intelligence together to improve operational efficiency and safety across a broad range of industries. ISIC, as mentioned earlier, is an accelerated platform for robotics and artificial intelligence. Here we see some more details of the hardware. The hardware is based on NVIDIA Converged Accelerator, which combines the computational power of GPU with the network acceleration and security benefits of DPU, all in a single high-performance package. This advanced architecture delivers unprecedented performance and strong security for AI-powered workloads. Here we see some more details of the signal processing performed on the GPU using Q5. In this slide, we only show the physical downlink share channel and the physical uplink share channel. All of the 5G NR control channels, for example, the physical downlink control channel and the physical uplink control channel, are realized on the GPU. They're just not shown in this feed, in this slide. In the PDSCH data path, we see transport block CRC attachment, code block segmentation, LDPC encoding, rate matching, scrambling, modulation, layer mapping, pre-coding, and resource element mapping. In the PU-SCH pipeline, working from the right to the left, we can see resource element demapping, channel estimation, MIMO detection, demodulation, descrambling, derate matching, hybrid ARQ, LDPC decoding, implemented entirely in software. The base-based signal processing pipeline implemented in CUDA is run entirely on the GPU. It delivers unprecedented throughput and efficiency by keeping all the physical layer processing within the high-performance GPU memory. The radio link control layer and the MAC and scheduler are hosted on a CPU. The mobile industry has been accelerating the use of artificial intelligence techniques in wireless communication. However, to a large extent, the current use of AI techniques in real mobile networks primarily relies on proprietary implementations and solutions. Global standardization has enabled mobile technologies to scale and flourish over the past decades. We anticipate that standardization will again play a key role in accelerating the AI applications to mobile networks. 3GPP has been studying AI-enabled radio access network in Release 17, including the principles, functional framework, use cases, and solutions. So next, let's take a look at this 3GPP study. As we discussed earlier, 5G networks are expected to meet the challenges of consistent optimization of increasing number of key performance indicators, including latency, reliability, connection density, and user experience, among others. Meanwhile, we have to address the complex system design and optimization issues introduced by 5G NR features, such as multi-radio dual connectivity, beamforming, and network slicing. Mobile networks operators find that traditional human-machine interaction very slow, error-prone, expensive, and cumbersome to handle these challenges. Artificial intelligence, including machine learning algorithms, provides a powerful tool to help operators to improve the network performance and manage the user experience. By analyzing the data collected and also processing the data autonomously to generate insights. These considerations motivated 3GPP to investigate the standardization aspects for 5G-enabled next-gen radio access network. Although most of the AI algorithms can be up to implementation, there are several aspects deserving studies in 3GPP. These include the signaling support for training and the execution of AI models, the data required by the AI models, potentially reported by the user equipment or collected from different parts of the network, and also the outputs generated by the models to be delivered to other parts of the network. So before introducing standardization support for artificial intelligence, it will be desirable to get some common understanding within the 3GPP community on the concept of artificial intelligence, and also the frameworks commonly used in the current or potentially future networks. Potential use cases and examples need to be discussed and to identify the AI-enabled features. Therefore, this study item aimed to study the functional framework for RAN intelligence enabled by enhancement of data collection through use cases, and also to identify the potential standardization impacts on current NG next-gen radio access network nodes and interfaces. During the study, 3GPP adopted a set of key principles to focus on AI applications with potential standardization impact. One key principle is that the detailed AI model, whether to use a decision tree or a neural network, is not within the scope of this study. Instead, the study should focus on identifying the essential information needed or produced by artificial intelligence models for each use case. Compared to the classical algorithm development, a distinct nature of artificial intelligence models is their learning nature. Therefore, the study investigated the standards impact of both model training and model inference. But the details of the training, such as the number of training iterations and how the training should be done, are not within the 3GPP scope. The study focused on AI functionality and the corresponding input-outputs. The input-output and the location of the model training and model inference functions were studied case by case. It was also agreed that the study should identify a general framework and workflow for AI optimization. But the framework and workflow are not supposed to be limiting. Thinking outside of the box is needed if a use case requires so. Last but not the least, 3GPP acknowledged that user data privacy and anonymization should be respected during AI and machine learning operation. This slide shows the functional framework for RAN intelligence identified in the study. Starting from the left, we have the data collection. It's a function that provides input data to model training and model inference. Examples of input data may include measurements from the user equipment or different network entities, feedback and output from the AI models. Going to the right, we have the model training and model inference functions. Model training is a function that performs the model training, validation, and testing, which may generate performance metrics as part of the model testing procedure. The model training function is also responsible for data preparations, for example, data pre-processing, cleaning, formatting, and transformation if required. Model training is a function that provides AI model inference outputs, for example, predictions or decisions. It can also provide model performance feedback to the model training function when applicable. The model inference function is also responsible for data preparation if required. On the rightmost, we have the actor function. This is a function that receives the output from the model inference function and triggers or performs the corresponding actions. Besides studying the high-level principles and functional framework, this study also investigated potential use cases and identified potential solutions for the use cases. The outcome of the study are documented in 3GPP Technical Report 37.A17. 3GPP will continue the normative work in Release 18. The objective of the normative work is to specify data collection enhancements and signaling support within the existing 5G architecture and interfaces for AI-based use cases. The selected use cases include network energy saving, load balancing, and mobility optimization. The rapid growth of 5G deployment brings the issue of high energy consumption, CO2 emissions, and high operation costs. Therefore, energy saving is an important use case. The optimal energy saving decision depends on many factors, including the load situation at different nodes, radio access network node capabilities, KPI or QoS requirements, number of active users, user mobility, cell utilization, among others. AI models can predict the energy efficiency and load state of the next period, which can be used to make better decisions on cell activation or deactivation for energy efficiency. So based on the predicted load, the system may dynamically configure the energy saving strategy to keep a balance between system performance and energy saving. Load balancing is another important use case. The rapid traffic growth and multiple frequency carriers utilized in commercial 5G networks make it challenging to steer the traffic in a balanced situation. Load balancing can be done by optimizing mobility parameters such as handover actions and handover parameters. Based on collection of various measurements and the feedback from the user device and network nodes, historical data, AI model-based solutions, and load prediction can improve load balancing performance to provide better user experience and improve the system capacity. Mobility optimization is critical for service continuity by minimizing the call drops, radio link failure, and unnecessary handovers. For applications characterized with stringent QoS requirements, such as reliability and latency, the quality experience is very sensitive to the handover performance. AI models can enhance the mobility performance. They can reduce the probability of unintended events, predict UE location, mobility pattern, and performance, and use the prediction for traffic steering. The 3GPP work we just discussed does not cover air interface. To reap the full benefits from AI techniques in next-gen radio access network, we must optimize the integration of artificial intelligence into the system design and realization, including the air interface. 6G standardization is expected to start in 3GPP around 2025. We have a window of opportunity until then to achieve an initial globally aligned way forward for integrating artificial intelligence into the design of mobile networks. Therefore, despite the fact that the design of the 5G air interface has largely been frozen, there's an urgency to get going to investigate AI-enabled air interface for 5G evolution in 3GPP Release 18, which is starting in Q2 2022. In this study, 3GPP will explore the benefits of augmenting the air interface with features that can enable improved support of AI-based algorithms to enhance the system performance, reduce complexity, and overhead. Of course, enhanced performance here depends on the use cases under consideration and could be, for example, improved throughput, robustness, accuracy, or reliability. By studying a few carefully selected use cases, assessing their performance in comparison with traditional methods and the associated potential specification impacts, the study will lay the foundation for future air interface use cases leveraging AI techniques. The objective is that we need to consider sufficient use cases to enable the identification of a common AI framework, including functional requirements and functional requirements of AI architecture. The study will also identify areas where artificial intelligence can improve the performance of air interface functions. We also need to characterize what is required for an adequate AI model characterization and description. This is to establish a common language in 3GPP. The study will also carry out evaluation to identify the gains of AI-based techniques for the use cases under consideration. As part of the evaluation study, 3GPP will identify the corresponding key performance indicators. So the ultimate objective is to have a better understanding of the gains and the associated complexity requirements. These investigations, functional framework, improvement areas, AI model characterization and evaluation, will pave the way for assessing the potential specification impact. This is critical for improving the overall understanding of what will be required to enable AI techniques for air interface. The study will identify or consider different levels of collaboration between the GNOB and UE. In this slide, we show a few examples of the collaboration levels. Starting from the left, we have the baseline. In this case, there is no collaboration between the GNOB and UE. The use of AI techniques, in this case, is purely based on proprietary implementation and solution. We do not change the air interface for AI models. Going to the right, we have the next level. In this case, there's still no collaboration between GNOB and UE. But compared to the first case, the difference is that here we may modify the air interface to facilitate efficient implementation based AI algorithms, such as introducing new measurements and reporting. At the next level, we have internode assistance. So here UE can get assistance from GNOB and vice versa. One such example could be the network may carry out the training of AI models, while the UE can download the AI models from the network. Then the model inference can be done at the UE side. The rightmost shows a sophisticated collaboration level between the GNOB and the UE. This level requires joint operation between the GNOB and UE. One example could be split learning between GNOB and UE. We will discuss a concrete example later. As mentioned earlier, this study will investigate the GPP framework for AI-powered air interface corresponding to each target use case regarding aspects such as performance, complexity, and potential specification impact. So the initial set of use cases include CSI feedback enhancements, beam management enhancements, and positioning. CSI feedback enhancement may target overhead reduction, improved accuracy, and prediction. For beam management enhancement, here we can look into beam prediction in time and spatial domain for reducing overhead and latency. And we can also look into how to improve the beam selection accuracy. For positioning accuracy enhancement, we can consider different scenarios, especially those with heavy non-line of sight conditions. So the objective here is to finalize representative use cases for each category by the end of this year. The ambition is that AI approaches for the use cases need to be diverse enough to support various requirements on the GNOB UE collaboration levels. Next, let's discuss a use case example, CSI feedback. In deployment without channel reciprocity, the base station needs the UE to estimate the downlink channel and transmits a CSI report in the uplink. CSI acquisition reporting has a significant uplink overhead. So to help reduce the overhead, the GPP has adopted codebook-based CSI feedback solution for 5G network. So the core idea here is that UE estimates the channel from downlink reference signal and feedbacks, for example, a preferred transmission rank, precoding matrix indicator, and the channel quality indicator to the base station. The design objective of CSI reporting in 5G NR is to ensure that the reported precoder accurately represents the dominant channel eigenvectors to enable accurate beamforming. In 5G NR, there are two types of codebooks known as type 1 codebook and type 2 codebook. So type 1 codebook utilizes a dual stage codebook. It's designed mainly targeting for single user MIMO operation. It has moderate CSI feedback overhead and it's relatively simple for UE to decide the preferred precoder. The precoder are factorized in a wideband matrix capturing the long-term channel characteristics and a subband matrix capturing fast fading properties of the channel. The type 2 codebook is designed mainly targeting multi-user MIMO. So in multi-user MIMO operation, the number of data streams is typically larger than the number of receive antennas at the UE site. So for this case, base station needs to apply transmit beamforming to suppress the inter-UE interference, which motivates the higher resolution Type 2 codebook for CSI feedback. Artificial intelligence techniques such as autoencoders can be used in CSI compression and reporting. So the basic principle of an autoencoder is to take an input, perform nonlinear compression by an encoder to a lower dimensional latent representation, and decompress the latent representation by a decoder to a defined target. So the principle is illustrated in the bottom figure here in the context of CSI compression. So here the UE estimates downlink channel state, and this is taken as the input to the encoder. The output of the encoder is transmitted over the air interface to the base station. The base station then uses a matching decoder to reconstruct the channel state. So here, the decoder, autoencoder model is divided between the UE and the base station, creating an internode dependency for model training, model management. VGPP delivers specification for mobile networks. Naturally, the study on AI for air interface will assess the potential specification impact, specifically for the agreed use cases and also for a common framework. So from physical layer perspective, we need to consider aspects related to, for example, the potential specification impact of AI model lifecycle management and dataset construction for training, validation, and testing for the selected use cases. Also, we need to consider the collaboration level specific specification impact, such as new signaling, means for training and validation, assistant information, measurement, and feedback. From protocol perspective, we need to consider aspects related to, for example, capability indication, configuration and control procedures, and management of data and AI models. Also, we need to look into collaboration level specific specification impact per each use case on the protocol stack. Interoperability and testability are critical for real deployment. Here, we need to study requirements and testing frameworks to validate AI-based performance enhancements. We need to ensure the UE and Genobi with AI solutions meet or even exceed the existing performance requirements. Okay, finally, let me wrap up the presentation. Let's recap the 3GPP timeline from 5G to 6G. 3GPP completed the first release of 5G specification in its release 15 in mid-2018, which laid the foundation for the commercial 5G deployment worldwide. Since then, 3GPP has been working on evolving 5G technology in its release 16 and release 17 to improve performance and also address new use cases. 3GPP recently approved the work package for its release 18, which marks the start of 5G advanced evolution. 6G is still in a research phase with a focus on the technology components and systemization. We expect that 6G commercialization to happen around 2030. So working back from 2030, we feel there's some urgency to get going. The standardization in 3GPP needs to start around 2025. We need to join forces to create and sustain the momentum. This can only happen with collaboration and openness. Here are some concluding remarks. AI is driving technology evolution and revolution. We believe that embracing artificial intelligence in 5G evolution towards 6G can fuel the next quantum leap in wireless. As 3GPP is ramping up AI items, AI adoptions in wireless will be accelerated beyond proprietary solutions in years to come. In particular, the standardization efforts will help achieve an initial globally aligned way forward about embracing artificial intelligence in mobile networks. The outcome will lay a strong foundation for integrating artificial intelligence into 6G when the 6G standardization starts in 3GPP around 2025. Opportunity to design 6G based on a data-driven architecture that will utilize enormous data to support AI across cloud, core network, radio access network, and devices. So together with ecosystem partners, we at NVIDIA are accelerating AI in wireless from 5G to 6G. The future of 6G is exciting. The journey towards 6G should be taken in collaboration with the academic community and the industry partners to have a globally aligned way forward. The future of 6G is in our hands. This is our time. Let's use our passion, our energy, our innovation, and our imagination to create a new G, 6G. We look forward to co-innovating for the future with you. So that concludes my presentation. Thank you for your attention. I welcome your questions or comments.
Okay, thank you so much, Xingqin, for the nice presentation.
Okay.
Thank
you,
with
Xingqin,
the
for
time,
that
I would like to
great
give it to my
presentation.
colleague,
We
Vishnu.
will go to the question and
Sorry, I cannot hear you, Thomas.
There is one question from Arthur.
Vishnu, proceed.
Like there's some issue with the connection. I cannot hear anyone. Maybe I can log out and rejoin and see whether they fix the issue.
No, it's okay. Can you hear me?
Okay, I can hear you.
Okay.
Can you hear me?
Vishnu, I think the
can hear you.
connection is
Yes.
not stable.
Okay, can you hear me better?
Yes. Yeah, you can take over, Vishnu, for the Q&A. Okay, just for the question, I guess maybe you can, Xingqin, you can address this question that Arthur has asked about the reference for the autoencoder-based CSI feedback. If you have like some references or some information related to that question.
I think if you simply search for CSI, autoencoder-based CSI feedback, you can find a lot of papers already published in this field. So it's not a new topic. Of course, it's a new topic for standardization, but from academic publication perspective, you can find a lot of good references on the internet already. If you have difficulty in finding those, please feel free to drop me an email. I can point you to a few classical papers.
Thank you, Xingqin. Sorry about that. I want to ask you a related question. You mentioned 3GPP TR as a reference. Do you happen to have that ready again? Could you, in one of the slides you were saying, or if you have, we can take it later about the 3GPP TR, which had studies on the use cases and the references. I think you mentioned 38 series something.
It should be 38817, but I can double check if that is not the right number.
Thank you so much. 817. I will look at that. There is a question from Ilmas. Ilmas, which software framework do you project on the computation need for AI? Which software framework do you use maybe in your project for computational needed for AI?
Yeah, that's a good question. Certainly, there are a lot of AI frameworks out there, right? TensorFlow, PyTorch, and I think these are all good frameworks. Of course, from an NVIDIA perspective, as we introduced at the beginning of this presentation, we also have a lot of AI frameworks from lower layer to up to application frameworks. So there's no, the AI framework that everyone should use because there are certainly different AI applications and use cases that will require likely different application frameworks. So I would say check your own use case and see which one really suits you best. And certainly, we welcome you to check out what NVIDIA offer in our internet. We have a lot of AI tools developed and made public.
Thank you so much. John is asking, can you tell if a nested ML model, for example, decision tree, result as an input for deep neural network falls into model training section of your flow? I suppose this is in reference to one of your slides where you showed this flow of training and the frameworks with the training, etc. So I guess that's the question is asking. But anyways, nested ML model as an example, for example, a decision tree result as an input for deep neural network falls into model training. You had a slide with the training and the flow. I guess that's where this question is coming from. Can we ensure the metrics are within the scope in such a case?
I think that's a good question. I don't have a clear answer for that one, but I want to mention that from standardization perspective, these details of the models are not within the scope because we don't want to limit the innovation of vendor-specific solutions, right? We usually only standardize the signaling, the input outputs, and the interfaces, and where the detailed models within the box should be left to vendor-specific solutions.
There are questions on data sets. I know in ITU we had this AI ML challenge where we have published many data sets. Arthur, you can look at that, but let me ask Xingqin, do you know any other data sets? There are public data sets, we are aware of that as well, but Xingqin, could you comment on the training data sets that you are using?
Yeah, that's a very good question. I think we all know that data set is a pain point for our industry. It's not an easy problem. Our industry traditionally tend to be not so open, and of course, there are a lot of difficulties in sharing these data sets, right? Although we generated humongous data, as I mentioned in the call, but that so many, constraints like regulatory constraints, user privacy issues, we just cannot share the data in our industry as freely as other industries like computer vision, right? So this is really a pain point. Although we do see some good momentum or movement in the past few years, trying to make public some data sets, just like you just mentioned about there are some data sets maintained by ITU. But my personal opinion is that these data sets are still not enough. So in this 3GPP study release 18 and maybe even beyond, we really hope to see more widely utilized data set will be created and maintained for the whole community. And also, meanwhile, we also want to emphasize that synthetic data set is also very important. So we just cannot generate data sets of all kinds for all AI machine learning use cases in the mobile communication. So from that perspective, we also need to rely on synthetic data set. So from that perspective, we also need to, for example, build digital twin of the real world to generate high fidelity synthetic data set, not just some oversimplified data set from some toy simulation setup. So going forward, we really believe digital twin will be a very important technology to generate synthetic data set to complement our shortage of real data sets in this industry.
Thank you so much. Yeah, actually, the ITU data set. Arthur, I would suggest you like take a look at our challenge data set. There are many open data sets there, and the simulated data sets, like Xingqin saying, there are several data sets available there, publicly available, including, I think there are some of them which has similar characteristics that you're asking. However, there is one interesting question on Shana. You mentioned about, I think in slide 11 or so, you did mention about Shana framework, and you did mention that it is open source.
Yes.
Can you talk a little bit more? Can you provide libraries for common? Do you provide libraries for common physical layer functionality? That's the question. I also want to ask you about the dependencies. Do you need specific accelerators to run this framework, or the students and our participants can run them on general purpose hardware? Could you please answer these questions?
Yeah. Let me take question one by one. So first, yeah, Shana is open source, and so you can download the code from the GitHub, and you can find, of course, it's an initial effort. We cannot implement all functionalities, but I would say many basic functionalities from link level simulations are there. And also, for example, example functionalities include like 5G polar code, LDPC code. These are very fundamental blocks for link level simulation. And also we implemented a few 3GPP models, like 3GPP channel models in Shana. So certainly this is an effort just start. So we really welcome the whole community together to collaborate and contribute to such open source project, even in our mobile industry. I know it's not easy, and it's not in the comfort zone of our mobile network industry, but we hope we can help make some changes towards this being more open and collaborative in our mobile industry. And then going to your second question regarding whether the China can be run on general purpose platform. Yes, you can run it on like CPU. Of course, it's just slower, right? You have to accept it's not accelerated computing. Yeah, but you can run it on CPU as well.
Thank you so much. That's great news. I personally will definitely take a look, and I know a couple of people who are here who would be quite interested to take a look at that as well. There is a question from Aldabaro. Let me take that. Can you please elaborate more on research and use cases for split learning? Yes, this is a question which I had as well. In one of the slides, you did talk about cooperative learning and split learning use cases, scenarios between UE and the network. So could you talk a little bit more about what is happening in 3GPP as well as in NVIDIA on what are the research and use cases for split learning between UE and network, especially using NVIDIA's tools? Yeah.
So from 3GPP perspective, this whole AI ML work is just starting. It's very difficult to see, okay, how we can. I think there's some skeptics, right, about whether this AI and machine learning, how helpful they are for AI interface. But we really need to start the work to understand the performance and the pros and cons to really build an AI native AI interface in the future, if possible. So split learning, I would say it's part of, it could be potential part of the scope of 3GPP, but it's, to be honest, at this stage, it's a bit far-reaching or stretch goal from standardization perspective. It's just so complicated. It requires so much signaling support, and also it requires a lot of testing and interoperability issues. So from that perspective, I would say split learning is more of interest from research perspective.
Thank you so much. In fact, I know Aldabaro does a lot of research in this space as well, especially in the area of digital twins. I want to ask you in slide 25. In fact, I guess he's referring to that slide as well. You mentioned standardized AI. What is standardized AI? What do you mean by standardized AI there?
Sure whether I mentioned standardized AI. To elaborate that question.
Yeah, I think the slide, if you see slide 25 around that, there is a figure which says the split joined operation somewhere, something like that.
Yes.
And there, yeah, so there, I guess it, I think there was something which you mentioned about standard AI models which can jointly operate between UE and network. That's fair question.
Yes. Okay. So for this joint operation, right? Let's say for this autoencoder based CSI feedback, you cannot just train a model at the base station side, or part of the model at the base station side and part of the model at the UE side. They need to work. They need to match each other. So they need to work jointly. So that's what I mean. Okay, you really need a AI model that could be exchanged between UE and GNOB. I'm not sure whether I understood the question and answered the question clearly.
There is question. Sure. Yeah. There is one more question on benefits. Nicola is asking about benefits. So I want to ask you, I mean, you mentioned about use cases. Nicola's question is whether there are benefits on the UE side. Well, maybe the end-to-end benefits are clear, but maybe for the UE side specifically, are there targeted benefits from using this AI? Especially, I guess the question comes from the fact that the AI models are trained in the network and deployed as inference in the UE. That's why probably this question is coming from. Are there any targeted benefits from the UE side?
In general, certainly AI ML techniques are beneficial, not just from network perspective, also beneficial from UE perspective. In fact, if you look at the smartphone today, they already utilize a lot of AI techniques within the smartphone. Perhaps a simple example, maybe going forward, that we mentioned beam management, right? Let's say if we can use AI ML techniques to predict the beam, then we could potentially save UE energy, because the current beam management framework is based on UE measurement and reporting. You need to measure the signal strength from different signals representing different beams, and then report this measurement to the network. And then the network can understand, okay, which beam actually used to communicate with the UE. So this framework, of course, requires UE measurement and reporting. That could consume quite some power if there are many beams in the system. If we can utilize the AI ML techniques to do a good job in prediction, in beam predicting, then we can save the UE measurement and reporting effort, which in turn can be translated into UE power saving, just as one example.
Mm-hmm. Thank you so much. I think that answers that question. Let me take this question from Jakob. He's asking, how can AI help in setting up managing? So yeah, so that's an important question as well. Managing operations, maintenance of deployment and planning of networks. I guess that goes very nicely with the digital twin concept that you explained. What are the, are there any further points that you would like to elaborate on setting up, managing, planning, operations of this network?
I would say that's a very good question. In general, the whole life cycle management could be quite challenging, and we usually need tools to help setting up these things. For example, from a video perspective, we have Fleet Command, which is a management orchestration framework, which can help setting up these whole AI models and maintaining them. But from a mobile network perspective, I think the story could be a little bit different. Now we have, potentially have models at the UE side and models at the base station side. And if we really want to go into the standardization route, this could potentially require some new solutions. And for that, at this stage, I don't have a clear solution for that. I think we need the whole industry together to work out the solutions. And hopefully, after a few years, we will get a clear understanding how to really do this.
Thank you so much. I guess we are running out of time. In fact, we are overdue, but thank you so much for staying patiently and answering all the questions. But this is not really end of the interaction. This is, of course, we are having real-time interaction. However, Thomas is here. Thank you so much for answering all the questions. Over to you, Thomas.
Thanks a lot, Vishnu, for the Q&A. And I would like also to take this opportunity to thank Xingqin for the wonderful presentation. It was nice to see the evolution of 5G and up to where we are going in 6G and the work in 3GPP in NVIDIA and all the cool stuff that we can use for research. I guess the challenge also can benefit from some of the tools and things that you have presented in the webinar. So thank you so much. Once again, I would like to thank all the participants who have joined today's session. We have not finished the interaction. We have about roughly 15 minutes for networking. So we will disconnect from here and we head over to the neural network. And everyone joining on the neural network, you can still keep on asking the questions. And I believe that Xingqin will answer some of the questions in the neural network. So thank you so much and see you. Thank you. Have a good day. Bye.
Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the satisfaction survey, connect with interesting profiles, or speak one-on-one using the chat and video function. After the 30-minute networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits and poster boards, and build your personalized AI for Good program. It was a pleasure learning with you today. See you at the next AI for Good.